It is now my pleasure to introduce Thomas Theis. He's the Executive Director of the Columbia Nano Initiative and Professor in Electrical Engineering in the Fu Foundation School of Engineering, Arts, and Sciences. He joined IBM at the T.J. Watson Research Center in 1978 to study electronic properties of materials and held various senior management and executive positions from 1984 through 2015. Among many initiatives he started at IBM were successful research programs in silicon nanophotonics and Josephson junction-based quantum computing. On assignment from IBM to the Semiconductor Research Corporation from 2012 to 16, he led SRC's Nanoelectronics Research Initiative, a private-public partnership funding university research aimed at new devices and circuits for computing. Let's welcome Thomas.
Thank you, Bill. I should say, you'll notice on this screen that I have in the upper left-hand corner, Semiconductor Research Corporation. I want to let you know that I still have a small part-time affiliation with IBM, providing advice to Dr. An Chen, who's the current Executive Director of the Semiconductor Research Corporation's Nanoelectronics Research Initiative. That's a program that I led for 4 years, and I'm happy to still be involved with it. And some of the content of this presentation will be based on that experience and the views that I've developed trying to guide a private-public partnership investing in new devices to take computing beyond the limits of the conventional field effect transistor. Now, that ties into the goals of the National Strategic Computing Initiative. From the workshop that was held last year, the NCSI fact sheet, computer system performance has increased at a steady rate over the past 70 years, largely through improvements in the underlying hardware technology, silicon CMOS devices for many decades. There are many possible successors, but none are close to being ready for deployment. And I've been working on that successor to the CMOS device for over 10 years. And none, that's true, none are ready. So here are my assumptions. There is a plausible path to an exascale machine. It's going to be pretty much based on current technology, continued evolution of silicon complementary metal oxide semiconductor, field effect transistor technology. I'll show you that in a minute. Things that I helped start, silicon nanophotonics, we call it, 3D integration, and more. Those things are already in commercial development, and they're not at the early research stage. The immediate challenge with exascale computing is to execute. But if you look at the strategic goals of NSCI, the first goal is to basically put the infrastructure in place and do the work to build that exascale demonstration system. If you look at the third goal, it's about exploring new devices and architectures that will take computing beyond the exascale. That is a component of the National Strategic Computing Initiative. And that's what I'm going to tell you about, where I think that's going. So I'll tell you very briefly about the opportunity and why we need it. I've heard a lot of talk at this meeting about new architectures for computing, reconfigurability, dedicated systems to execute convolutional neural networks, algorithms, and so forth. Lots and lots of discussion. This is ongoing. This is established. But it's all based on the established technology. And what I want to tell you about it is the growing research investment in a new technology base or bases, more than one technology, that might allow us to simultaneously develop several new devices and new architectures. And that's the unexplored, still very much unexplored research landscape, the co-development of devices and new architectures for computing. I want to start here, though, by giving you some history. This is a long view. This was a paper published by IBMer Rolf Landauer, a very famous physicist and really, in many ways, a pioneer of the physical understanding of computation. And his colleague, Bob Keyes, had taken data from sort of random publications over the years that gave a clue as to how much energy was being burned or dissipated every time a logical device switched. And he just plotted these over decades. As you can see, there's an enormous drop there, many, many, many orders of magnitude. So in 1988, when Landauer published this, he extrapolated it onward, forever, downward, towards the energy at which random thermal fluctuations would start to cause random upsets of the logic, the KT limit, some people call it. It means you have to have, if you want to compute at, say, room temperature, you have to have a device that stores much more energy in the device to distinguish a 0 and a 1 state than is much larger energy than the random fluctuations in energy that are going on all the time in the environment. You could cool things down, but then that takes refrigeration energy, so it's hard to get around that. But that isn't what stopped progress. These are data points from IBM, from Intel, up till rather recently. And then if we extrapolate the values from the 2000, or just take the values from the 2013 International Technology Roadmap for Semiconductors, we see there was not only a sharp break in these trends, but the foreseeable future is just much slower, still improvement in the energy efficiency of computing, but much slower improvement. What was going on there? Well, we have a clue. There was very rapid reduction in the operating voltage, the voltage swing that determines 0 and 1 for a while. But then it became harder, and I'll tell you a little bit about that in a minute. And there was an attempt to sort of make up for that by doing faster shrinks, faster introductions of technology generations, but it didn't really help. And that's sort of where we are. That minimum energy for devices that we might have, if everything continues in its current line, in 2028, is still orders of magnitude larger than the minimum energy that nature would say we have to use, we have to store in our devices. These are all the absolute minimum size device. Practical devices and with the wires in practical circuits would store much larger energy than what's shown on this chart. Now, that voltage problem, the inability to reduce the voltage, led to some very big changes. Many of you have probably seen this chart. If we look at, is this a laser? Never mind. Look at the green line. Integration densities continuing to increase. The slope goes up because more and more of the transistors are memory now, and that is denser. But clock speed, the blue one, plateaued between 2003 and 2005. And that had to do with the inability to reduce power supply voltage and the need therefore to constrain the power that was being burned, because otherwise it became economically unacceptable. You can't have a cell phone that gets hot in your hand against your face. You can't have a game machine that sets the curtains on fire when you forget to keep it away from them. And you can't have servers in a data center that cost more to power and cool than the capital cost of replacing them on a regular basis. And people start to say, no. And in fact, there was some of that going on in the marketplace, and manufacturers had to pull back a little bit on what they could do in clock speed. And also we see, at least measured by instruction level parallelism, not only did power plateau, but also some of the easy invention within the standard CPU, the so-called von Neumann architecture, also was saturating. So a lot of saturation going on there. But integration continued. But what happened is that, I'm not going to try to teach you this. I just want you to know that it is physics, okay, that made these changes in the industry. That's all I want you to know. But think of a transistor. It's a switch. There's a gate voltage, V sub G, and to turn on and off the current between the source electrode and the drain electrode, you have to have a certain voltage swing. It turns out that at room temperature, that voltage swing for physics, fundamental physics, and engineering, practical engineering reasons, has to be about a volt. So if you have a 6-volt power supply, you don't really worry about that 1-volt penalty you have to pay to really turn the device off hard. But if you have a 1-volt power supply, you're stuck. You can't go lower. And let's ignore that. What happened is, with the voltage swing already reduced to about a volt around 2003, 2005, the FET was getting close to the fundamental limit for operation at room temperature or 80 degrees centigrade, whatever the operation is. But again, based on key measures of integration density, the industry kept increasing the integration density. Now, there is a slowing on this chart, but if Moore's law is about increases in integration density, this chart does not show any dramatic reduction in the rate of progress. In fact, I heard a speaker or a panelist yesterday say, oh, Moore's law is going to end in the next 2 or 3 years. There's no evidence of that. In fact, I'll tell you that the engineering teams are quite confident they can keep things going for another 10 years. That means another couple cycles of technology introduction. But if you look at it over a 20-year period, squint at those data points, by these key measures of integration density, the gate pitch, the minimum gate pitch, the minimum narrowest wiring pitch, SRAM density, things are slowing down very gradually. So here's the brief summary of what happened without getting into the physics, but it is physics. To keep aerial power density and total power within economically acceptable limits, what the industry had to do is freeze clock speed. And they also, and this is the reference there that you see, they also had to slow the introduction of cores. Now, of course, that also allowed them to put more cache on the chip, which is a good thing. And of course, the software community couldn't really figure out how to effectively use all the cores that could have been put on the chip. So those might have been the driving factors. But I'm telling you, physics, the economics of heat removal, would have stopped it anyway. So to escape this status quo, some of the companies in the microelectronics industry pooled their funds and tried to get new research going. They worked with the national funding agencies, National Science Foundation, National Institute of Science and Technology, DARPA, and tried to get new research going on in the university community that would look at new devices and new architectures for computing. So one of these programs that I helped found was the Nanoelectronics Research Initiative. We founded in 2005. We actually started work in 2003, right about when those clock speeds started to plateau. It's been running now for 10 years. It was refreshed after the first 5. And the mission is to demonstrate, at this point, non-conventional low-energy technologies for computation. So it started out with, what's the next switch? And it's moving towards the, well, let's not worry if it's going to be a drop-in replacement for the field effect transistor, but what could take computing forward? 3 multidisciplinary, multi-university research centers running right now. Around 2013, NRI was joined in the focused exploration of beyond CMOS devices by what was the former Focus Center research program. That was completely refreshed as StarNet. That's been running for a while, and they're funding 6 multidisciplinary, multi-university centers. And 3 of those centers are, like NRI, tended to be strongly device-focused, materials, new devices. But 3 of them are exploring new architectures for computing. Now, I want to briefly, so 10 years of device exploration, where are we? Again, I'm not going to teach you physics, but let me tell you a little bit about a process that we have. We call it device performance benchmarking. And this is a normal thing to do for established technologies. It was quite difficult. Many people over several years managed to figure out a coherent way to do it for exploratory devices, some of them just conceptual, not even laboratory demonstrations at this point. I won't go into that, but let me just show you some results. What a mess. Look at all those devices. The ones in green are our good old high-performance CMOS technology, and CMOS low voltage, so a different variation that's been developed for very low power applications. And we're plotting energy versus the delay on this chart. Now you see a bunch of blue dots, and those seem to be competitive on the energy versus delay line. Some of them suggest, according to this, they could be better than the field effect transistor. Some in red look much worse. Those happen to be magnetic devices, where the digital state depends on the polarization of a tiny magnet in most cases. And I won't go into the others right now. Why are the blue and green ones fast? Well, they're all transistor-like, so they all depend on the rate at which a current flowing through one device can charge the capacitance, let's say the gate and wire capacitance, of the next device or devices in the logic chain. And nature says the intrinsic delay can be set in the picosecond range for semiconductor systems and metal wires. The magnetic devices are much slower to switch. They have an intrinsic time constant too. It has to do with the spin precession of the magnetization vector in the internal magnetic field of the magnet, the ferromagnet. So you start spinning up, and then you have to spin down and end up in the other polarization. There's just a speed limit to that. But they are very interesting devices the magnetic ones, and also the ones in yellow, the ferroelectric ones, because they retain their state when the power goes down. These are really memory devices trying to be logic devices. And that produces some very interesting possibilities. So here's some takeaways from 5 years of this work. As the device models that we're putting into this thing have improved, the estimates of the device attributes tend to become more conservative, but hopefully more accurate. And no clear winner has emerged. There's nothing in a laboratory that can compete, nothing working in a laboratory. Those blue points that look competitive with the green ones are really extrapolations of what ought to be possible based on what we know. But no one has a laboratory demo. But the interesting thing to me is that new device concepts have continued to emerge, suggesting that more, perhaps many more, devices are yet to be invented, which is why the university research is so important. No company could begin to explore that enormous research space. We just don't know now what works, but we're starting to understand. So how long does it take to truly understand the potential of a promising device concept? So here's a different device that people have been working on for quite a while, called a band-to-band tunneling field effect transistor. So you see the arrow there on the left going through what is an energy barrier, a tunnel junction. And that junction is designed in the device to be thin enough that the carriers can, when the gate voltage is the right value, tunnel right through without too much resistance. When the device is off, though, that tunnel barrier becomes much wider, shuts the current off. That's a very different switching mechanism than that field effect transistor I showed you. It's not subject to the same limits. It should be possible to turn devices like this on and off with voltage swings of tens of millivolts or maybe 100 millivolts. That would reduce the power to do the same thing logically at the same speed, if these were capable of high speed, by a factor of 100, which would certainly get us out of the power performance block or bottleneck that we're in now. So again, don't read all the words on this chart. But this started in 1989, the first paper was published. And there was no pickup on this until about 2005. Some work at IBM triggered a lot of interest. And then these programs, the Nanoelectronics Research Initiative, and now the StarNet program under the Semiconductor Research Corporation, co-funded with DARPA and with the National Institute of Standards and Technology and with National Science Foundation. These programs have generated a lot of research and a lot of understanding and a lot of invention. But the problem is, although new variants of this device continue to emerge to this day, right now, they don't work. They work. In fact, they look really interesting if you want to make a tiny, tiny electronic sensor to measure very small changes in a current to perhaps do biosensing. So they're going to have applications, I think. But they don't allow, at the only time you get this abrupt turn on of the current is at currents that are too low to be useful for electronics. As you get to currents that are high enough to be useful, they don't work any better than a conventional CMOS field effect transistor. And we don't know why. The fundamental research still has to be done. So it was kind of interesting when I heard someone talking yesterday about TFETs and other devices as if they were real. Well, they're real. They're just not ready for prime time. And it is, I wish I could talk about why they don't work. I have some ideas. People have some ideas. Sorry. But we're just really not sure. There's two competing thoughts there. Anyway, Magnetic devices, I mentioned, they're slow, but boy, they're kind of interesting. There's two exciting sort of branches of frontier work right now. Instead of switching a magnet polarization with a current or an applied field, which is going to be very power hungry, can we just switch it by applying a voltage? Magnetic random access memory is an emerging memory technology. It's very exciting. You can put it close to the core. You could get a lot of cache. It would be denser than SRAM, might be as fast. Very cool technology. It's emerging slowly. The question is, how small can you make the devices? But there's two approaches that we might be able to turn that into a much lower power device and a much faster device. I won't go into those, but it's exciting frontier research. Well, I'll go into this one. Here's an attempt to take some of that science and turn it into a 3-terminal voltage-switched magnetic random access memory. And that could be a lot faster and a lot lower power than MRAM, which is than the current generations of MRAM. And that would be very exciting because those are already fast and low power. So here's an assessment of current research. The rate of invention of new device concepts is increasing as far as I can tell. Nature is wide open. We just have to figure out what the possibilities are. It's highly unlikely that the new switch, if that's what you're looking for, is out there. It's highly unlikely that I think it's highly unlikely that CMOS is the end of the road. Many engineers of my age have decided to retire and not worry about it. But I don't think it's the end of the road, and I also don't think any of the exploratory devices that are currently on that benchmarking chart that I showed you are going to be the one that replaces CMOS. I think there's a whole lot more to do. And the other thing that we absolutely know now, it made sense if we'd thought about it 10 years ago, but we absolutely know now that if you try to change the physics of a device, even if it's transistor-like, even if some gating voltage switches the flow of current in a channel, that would be very transistor-like. It's not going to behave in a circuit exactly like a field effect transistor. So we know that devices and circuits must be co-developed. But beyond that, some of these devices may have characteristics that are particularly well suited to new and emerging architectures for computing. That's the exciting thing that's just starting to be understood. So let me give you just one example of a broad class of what I think you all know is an increasingly important class of architectures, neural network architectures, particularly of interest, I would say, because deep learning algorithms are now the best algorithms for many classes of problems that are increasingly important, pattern recognition, matching, and so on and so forth. Here I just want to show you just a very simple picture. This is actually from a publication by Kaushik Roy's group at Purdue. It doesn't matter. I could take any picture of any schematic of a neural network. Very simple. And the point is that computation in each of the nodes of this network is very, very simple. It really doesn't make sense to if there's an alternative, if nature provides us with an alternative, to implement this with transistors. It doesn't make any sense to try to do this with CPUs, GPUs, or even FPGAs. They really don't map, maybe FPGAs, but they really don't map that well to the architecture that's suggested by the algorithm. The question is, can that computation in those nodes and perhaps the weighting of the connections in the synapses, can that be done by very simple, compact, and ultimately very small devices? So people are really thinking about that now. Here's the schematic. We know that nature's already figured this out, but of course we do not know how neurons really work. We just have these heuristic ideas that have resulted in these artificial neural networks and inspired algorithms like the deep learning algorithms. So we don't know what we're trying to build, but if we just focus not on what nature's done, but on what is suggested by our algorithms and the neural networks that have already been built, and we know they can do useful things. Here's what one group, again, Kaushik Roy did I say, I'm sorry, Notre Dame? Here's what they suggested. The blue objects are really very simple, compact devices. If you look at this paper, you'll see there's no reason they can't be tens of nanometers in lateral dimensions. And the devices up top, connecting the cross-point array, those are memristors. Those would store the synaptic, the weight or the strength of the synaptic connections. So this is very much frontier research. These are nanomagnetic devices, and guess what? The particular nanomagnetic devices have been studied that are referenced here in this conceptual network, have been studied. People are trying to build them as part of the Nanoelectronics Initiative and also as part of the StarNet program. But they're not very good working devices in any laboratory at that time. So we have people rushing ahead to design new architectures based on devices that really don't work very well yet. So one of the things, here's another example. This is a different example, but again, based on nanomagnetic devices that have this property of storing the information and in a non-volatile way, and therefore, the idea is to organize them correctly. You're not just putting memory and logic into close proximity; they are in the same device. So we have these research examples, and they really suggest what is, I think, the truly unexplored research landscape: new devices and new architectures, the co-development. I'm not going to tell you everything that came out of our workshop, but it took a couple years' work. But we just got a program in place just as I was leaving the my assignment with the Semiconductor Research Corporation. This program is now led, among other programs, by An Chen. And we talk on a weekly basis, so I'm very proud of the program. I will not go through the various projects, but this is pretty typical of what the Semiconductor Research Corporation does. Here, it's partnering with the National Science Foundation. It's funding research across the whole United States. Each of the projects pulls many university groups with various disciplines together, and they explore very, very unconstrained research. I like the one there you see up on the upper left, energy efficient computing with chip-based photonics. This is a way of computing with coupled optical oscillators. If you have an array of oscillators and there's some coupling between them, the dynamics has some great similarity to the dynamics that people have observed for neurons in the brain. And that dynamics is believed to be related to computation, well, fundamental to the computation that the brain does, and things like pattern recognition. So this is an exploration of a way to do that in a system that would be perhaps ultra-fast, compact, we hope. These are nanophotonic oscillators. They're very small. And we hope because each of these programs couples people that are tops in the architecture field with people that are tops in the hardware device research field. We hope that they will break new ground. We hope all of these programs will break new ground. Some of these programs are still aimed at that low voltage, ideal high current switch, which would be the sort of the drop-in replacement for the FET. But the largest programs here are really looking at new devices and new architectures. Now, if the tunnel FET started in 1989, research, and we're still working on it, this is not going to impact the Exascale computing project. But I do believe research will come out of this that can take computing, believe it or not, as hard as it will be to build the Exascale machine, far beyond the Exascale. But we need to have sustained funding of this kind of research. Thanks a lot. This is my conclusion. Once you step outside the FET devices and circuits box, and I should have added the von Neumann architecture box, there is a lot to explore. The game is not over, even at the fundamental hardware level. Thanks a lot, everybody.
Thank you. We have time for a few questions. And if you don't want to use the microphones, you can go through the program to submit a question, and I'll be checking out for them. Go ahead.
So they declared that the ITRS roadmap is dead because they can't scale beyond 7 nanometers. So it's ITRS 2. And want your thoughts on perhaps this is a good thing because maybe it's philosophically how we're looking at this has to change, and by ending conventional thought as in the ITRS, that maybe a new ITRS thought mechanism is going to spur new innovation.
Yeah.
And just as a follow-up to that, perhaps the device is driving to, as the World Wireless Congress says, there's going to be trillion front-end radios in 2018. So is Exascale, where now we're dealing with trillions of devices instead of trillions of computations on large amounts of data, what's the potential impact on architecture?
Well, that's, okay, so first, I think the question, I hope I paraphrase it properly, was the ITRS basically, as it had been running with this projection of where CMOS is going to go and what you need to do to keep it going, ended in 2013. There won't be a refresh of that. It's been rebooted. Now the focus is much more on what people call more than more. How do we, what is the research that needs to be done to extend, broaden the applications of the device, of modern microelectronics. I have not personally paid close attention to what's coming out of that. I think it's a very useful thing to do, and I would say that the same people who are guiding these programs like the Nanoelectronics Research Initiative and the StarNet program are in fact the people who are providing the front-end input to this kind of a road mapping. In fact, An Chen, I mentioned as the director of the Nanoelectronics Research Initiative, was heavily involved with all of these recent iterations of the International Technology Roadmap for Semiconductors. So this thinking that I've shown you in my talk is not disconnected from the thinking on the ITRS. The ITRS says it's going to be a 1.5 nanometer technology generation. That really means that the gate length is something like 7 nanometers. But the real issue is the companies that are doing this lost interest in the ITRS. They did not find that it was very helpful because things are slowing down, and the way they're progressing is much more invention rather than let's just shrink as an engineering problem what we made 2 or 3 years before. And so it was just becoming less predictive and useful. I think. Also, all of these companies are unfortunately making a little less money each time they invest $1 billion to roll out a new shrunken generation, smaller generation of devices. They don't increase clock speed. They get some power gain. They get some reduction in power because the wires connecting the devices are shorter, the devices are smaller, store a little less energy. But they don't get the very big gains in performance. It doesn't open up the obvious new markets. So being the market leader is much less important than it used to be. The market leaders are not necessarily the companies that are leading in the new applications. So this, I think, is the economic force that is slowing the progress. I'm sorry.
Over there.
Yeah, too long an answer. I didn't get to the second part of the question, but go ahead.
What do you think about the potential for, I'm over here, the short guy in the wheelchair. What do you think about the potential for memristors to help with the kinds of problems that you're describing?
Well, so first there's resistive random access memory, which is what memristors really are. And that's very interesting because basically you can build it with low temperature processes. That means you can build the silicon, build your core, and then you can put a lot of really dense memory on there, maybe in multi-layers, as people are already doing like flash memory. So I think that there's a lot of, I talked about ferment new ideas in the logic space. I didn't talk about new ideas in the memory space. There's at least 4 or 5 memory types, very distinct memory types that are moving along very rapidly. RRAM is one of them. Now, the use as a memristor, that is, build the device and set it up under conditions where it will have a memory effect, that the resistance of the device will depend on its history in the circuit, what current flowed through it, what voltage was applied, is, as I said, of great interest for these so-called neuromorphic systems. I think, and I'm not a deep expert here, but the problem is what people are doing in the machine learning community, running convolutional neural network algorithms and so forth, is all being done by train the system, whatever the hardware, it's all being done by train the system, set the synaptic strengths, or set the connection strengths, and then solve the problems. Just leave the system fixed. It's really an unsolved algorithmic or architectural problem, since the two are intimately connected, as to how the system should learn on the fly. There are ideas about that, but show me a commercial application. Show me a system that's really doing something very useful. When that happens, then you will see a much bigger research effort and much more rapid development in this space where the memristor ideas come into play. That's my personal view. I'm not a deep expert.
Well, thank you. Let's thank both of our speakers.